Alright, so today we are going to discuss area distortion and orientation. So a little bit of linear algebra, and then we're going to go into orientation. So to begin with the definition, let's say we have a matrix like so. And if we have a function such that given bases defined by the following basis vectors, suppose we have, and this is a vector space V, and this is a vector, or yeah, these are vector spaces. Specifically, we're considering them to be two-dimensional subspaces of R3 because we work in R3. Then we have a function like so associated with this matrix in such a way that so you can think of yeah. So you can think of this matrix as essentially containing the relationships between the basis vectors. So one might be wondering what the point of this function is. And we have a quantity called area distortion of the function g, which we denote by g with double bars around it, and it does not depend on the choice of basis. So no matter what the basis vectors are, as long as it's the same subspace that the basis defines, this should remain the same. Okay, let me just quickly write this down. So remember that the cross product of two vectors is a vector. So we're taking the magnitude of that resulting vector, and same for the bottom. So we propose that this quantity does not rely on the choice of basis. So why don't we prove that? Another basis of V may have a basis of the form like so. So what happens if we plug in this basis, replacing V1 with this and V1 with that? So here's what we get. And we can use like various properties of cross products. I could go through it, but I think it would be best just to skip to the result of what we get. and that ends up being and of course we can cancel these out, and we see that this quantity remains invariant under choice of basis, so long as it's the same subspace. So what is this area distortion capturing geometrically? Well, let's say that we have a subspace, two-dimensional, okay, that doesn't work, of this form, and we're going to send it by G to a subspace, like maybe like this. Now, what the area distortion essentially captures is if we have a pair of vectors in the subspace, and the two form a parallelogram of perhaps area A, then they're sent to, maybe one is sent like this and one is sent like that. The area of this parallelogram is going to be the area distortion times the original area. So let's make this clearer. That's essentially what the area distortion captures here. So hopefully that should sort of help us understand what the area distortion is doing. So furthermore, we have that, let me just write down proposition. The area distortion is the absolute value of the determinant of the matrix representing G, I believe it was that, with respect to WRT, any choice of orthonormal bases. Orthonormal bases for V and V. So, first of all, if we take a look at this by definition, right up here, we have, that should be a plus, and we can use the same cross product properties to obtain this expression. And one might note that AD minus BC might look a little bit familiar. That is the determinant of our matrix A. And then we have the cross product of those two. So what do we get? Now let's look at this area distortion. So we got this, and we already know how to represent this. So we get, remember to keep the absolute value times, because we have this, over, and don't forget this. So, and note that since these are orthonormal, the cross product of these two should be a vector of length 1, because this has length 1 and this has length 1, and they're orthonormal or orthogonal. Same thing with this. And therefore, we have proven the proposition. So now let's talk about orientation for a subspace, a two-dimensional subspace of R3. So an orientation for V is a choice of a unit normal, which we'll call N, to V. So we say that it is positively oriented if, oh wait, I messed that up. The cross product normalized will, of the two basis vectors, equals the normal vector. So otherwise, it is called negatively oriented. So let's say we have, let's keep it simple. Let's have a subspace like this. And let's say that we have basis E1, E2, X, Y, Z. If we have an orientation choosing a normal vector like this, then it's positively oriented, because let's call this N1. And you can do like the math, but that's how it ends up being. But if we have this N2 as our orientation instead, then we find that normalized cross product equals negative N2. So now let's think about orientation preserving maps. So we say that G is orientation preserving if this basis of phi is positively oriented, then the basis given by applying G to the basis is also positively oriented. Furthermore, we must have that matrix representing G has positive determinant. And these conditions are equivalent, so if it satisfies one, it satisfies the other. So that's basically it about orientation for linear subspaces. So let's move on to orientation with regard to surfaces. So we need to define a normal vector to a surface at a point P is a vector in, we'll call it N, in R3 that is orthogonal to the tangent plane of S at P. So that means the inner product equals 0 for all V in the tangent plane at P. A unit normal vector is simply a unit length normal vector, or it can also be an orientation for the tangent plane. So let's draw this out. Let's say we have a surface like so. And maybe we're concerned with this point P here. And it has a tangent plane. A normal vector would be perhaps a vector like such as this. Let's say we have some v1. You can see it's at a right angle, and for v2 it's at a right angle. So the normal vector is orthogonal to the any tangent vector in the tangent plane. So we can actually find a formula for a unit normal vector at a point P. If we have a coordinate chart as defined in the previous video, if you consider its partial derivatives, then we have that the normal vector where sigma of q equals p. Now let's talk about a vector field. Vector field on S is a smooth map, which we'll call V, from S to R3. So it's a tangent field as a subcategory if the resulting vector is in the tangent plane at the point for all P, for all points in the surface. And it is called a normal field if for all points in the surface, the vector, the corresponding vector, is normal to the surface at that point. So, now we can define an orientation for a regular surface, which is a unit normal field on it. So a regular surface is orientable if there exists an orientation for S. So an orientable surface equipped with a given orientation is known as an oriented surface. And we can say that a surface patch sigma is compatible with the orientation if this holds true. This holds true. If this is in the orientation. So let's say that you know what? Let's say that S is a compact regular surface. Compact regular surface. Then we must have that R3 minus S, which is all points in R3 that are not in the surface, has exactly 2 path-connected components. And remember, a path-connected component is essentially a set such that any 2 points, you can draw a path between them. Or, yeah, from one to the other. So, one component, the interior, is bounded, and the exterior is unbounded. I'm going to skip over the proof of this theorem, but and I'm just going to move on. Now, just like how maps between subspaces can be orientation preserving, we also have that diffeomorphisms can also be orientation preserving. So, and these are 2 oriented surfaces. It's called orientation preserving if for every point in S DFP is orientation preserving by the definition of a linear subspace for a linear subspace. So you might be wondering, is there a surface out there that is non-orientable that we can easily visualize? And my answer to that is yes. The most common example of that is the Mobius strip. Oh, yeah, I think I drew it right. Hold on. my god, I'm gonna have such a hard time drawing this, but okay, I think I got it. So let's take a look and see what happens if we try to impose an orientation on this surface. So we choose a normal vector like that, so that's fine. So what happens if we extend it further? Now this is sort of, oh, this is sort of, and as you can see, at the same point, there are two normal vectors with this continuous vector field, and that's kind of a problem. We can't really have that happen for orientable surfaces. And for that reason, the Mobius strip is non-orientable. I know the drawing is kind of bad, but hopefully that sort of clears things up. That's basically all I have for today. So hopefully you took away something from this, and thanks for watching.